Hello, this is Nate Fosse. You should be able to hear me. Um, I'm not sure if you're able to see my video, um, but you should be able to see the answers. Okay, great. Thank you. Great, fantastic. Thank you. Okay, so we did our problem set this past week on simple linear regression, and we're just going to review basically the answers here and sort of the logic as we sort of. I hope you're getting used to the pattern of the course. Um, so let's just start with the first, first part one, where we review the key statistical concepts. And I just want to emphasize that I hope you're seeing a pattern here in terms of how to answer the sort of the flow of the questions. You basically, the main point is that when we answer questions in the course, we basically emphasize interpreting output. And what do we mean by output? Well, basically, I'm emphasizing this what I'm going to spotlight here, which is this basically this output right here. And typically, this is what we're going to present in terms of the R format of output, which I show every Monday, which is in your console. I want to emphasize that we typically give you the context for interpreting and understanding these answers. That being said, there's always, interpretation is often a key format or a key aspect of understanding and interpreting stats. So sometimes understanding a bit more about the data or more about your role and more about the mission helps to understand perhaps more about the role of answering these questions. So I'm going to clear all my drawing here, and that's my sermon of the week, sermon du jour of emphasizing sort of, I think, I guess, just the role, the centrality of interpretation. So let's go to this first question. I think you'll see sort of what I hope to be a logic in terms of answering the question here. We just basically ask, what are the values of the regression coefficients? So to break this down, I always emphasize sort of dissecting or analyzing what are the components of the question. Well, clearly, when we talk about regression coefficients, we emphasize some background knowledge here. What do we mean by regression coefficients? Well, here we're emphasizing the fact that when we talk about coefficients, you should take a look at the output here. We have what is called this intercept, and then we have the slope for the regression line. And what this does is essentially describes the association that we have between two variables, our predictor variable, which is always given to the right of the formula, and then I'm sorry, I think I can hear somebody's background sound. I want to make sure that everyone's muted. Okay, good. All right, thanks. Then we have the slope here. And the slope isn't actually referenced in the output. If you see my little highlight here, you'll see that HIV is the slope, and it is the predictor variable. And, oh, I want to say, sorry, I distracted myself. The predictor variable is to the right of the output, and then to the left of the output is, sorry, to the left of the tilde. I'm sorry, here's some background noise. Just want to make sure everyone's muting themselves. Anyway, to the left of the tilde here, just as we have it typed in our syntax, we have the outcome variable. And we know that we're looking at the predictor variable because we see the coefficient or the slope for the predictor variable. And then we see the intercept for the predictor variable. So typically you'll see only the slope for the predictor variable in question. You won't see the word slope in your output, but you will see two kinds of coefficients. You'll see, in essence, the intercept, and then you'll see the slope. And then when we have sort of an optional week, we do emphasize multiple regression, where we might see multiple kinds of slopes. But the main point is, when you talk about simple linear regression, we're talking about a linear association between one predictor variable, HIV, and then its intercept. And that's all you need to describe a line. If you remember from algebra, y equals mx plus b. But the main point is that the intercept is the value of our outcome murder rate when it's the value of our outcome when y equals 0. When x equals 0. So it's actually if we kind of imagine sort of in our heads a scatter plot, what is if we set everything to 0? So if we imagine a country with no HIV cases, what would be the hypothetical murder rate there? Well, we have the hypothetical value. Sometimes it makes sense, sometimes it doesn't. And so here we have the answers here, and we can sort of see the question here. And it might be kind of the main reason I emphasize interpreting the output here is that, the answers can be sort of tricky here. We're giving you numbers and answers that seem reasonable, and it's kind of a red herring. We give you some red herrings here. It may appear that the slope cannot be determined from the information provided. In fact, it can be. And in fact, we have both the intercept and the slope, and that's actually evinced by the answer to the first option here. So basically, if you think about the logic of answering the question, just know some of the background knowledge, like what is a regression coefficient, and write down what you know and try to answer for yourself before you look at these options. That's typically the way I would answer these questions. And then we ask for you for the equation for the regression line, and we give you some options here. Remember, I emphasized and I defined when I'm describing the output what is the intercept and what is the slope. So here, basically the answer that you should come up with is our y outcome, which is equal to our intercept plus the slope times HIV. Well, what is that? What's our intercept and our slope? Well, it looks like it's this one right here. This is the correct answer. Of course, I'm answering this off the cuff. I want to make sure, of course, I'm right here. So I'm the instructor. I should know this, right? So this is the correct answer right here. And we know this because the intercept is when we set our slope to 0. So it's and basically after this, it's a plug and a chug. So what is the slope here? The slope is defined by how much does the murder rate, or our y variable, increase for every 1 unit increase in our x variable. And I'll say that again. The slope is the value here, and it is how much our y variable increases for every 1 unit increase of our x variable. And what is that here? Well, a value of 1.15 means our murder rate increases by 1.15 for every 1 unit increase in our HIV rate. Now, of course, these are both different kinds of rates, so context is key in interpreting what is the substantive significance of the slope itself here. You could debate about whether or not that's important. It's sort of, I think, if you think about murder rates, you might want to say, well, any kind of murder rate in a country is probably relevant, and we don't really want to have any murder rates. So even no matter how small that slope is a positive slope is something we really wouldn't want to see in any kind of association. But again, context is key. Suppose the percentage of people with HIV within a country, question number 3 asks, suppose the percentage of people with HIV in a country is 50. What is the expected murder rate per 100,000 people based on the regression equation? Round your answer to 2 decimal places. You should have a multiple choice option there. The point is that when I emphasize what is a plug and chug, or what is a plug and chug here, I'm just emphasizing the fact that you take the regression line and you take the equation for the regression, and then you insert the value for 50 for the HIV. So you take HIV times the slope plus the intercept, and then that would be the expected murder rate per 100,000 people based on the regression line. Or essentially what we're asking you to do for question 3 is to derive the predicted value given the x value. What is the y value that you'd expect? So here, basically the answer is quite simple. It's just it would be 1.15 times 50 plus 19. You should come up with an answer around 77, maybe 76.8 something, 76.86, something in that ballpark. I say in that ballpark because you could round at different points. You could round each value to 2 decimal places, or to keep them intact. So anywhere within 76, 77 should be correct. And let us know if that's an issue, but it shouldn't be. Question 4 should also be multiple choice. It is again a question where we ask you to round to 2 decimal places. We ask, now suppose the country, the percentage of people with HIV in the country is 0, parenthesis 0. What is the expected murder rate per 100,000? Right, what is the value of murder rate based on the regression equation? Round your answer to 2 decimal places. Now we're just plugging and chugging a different value. Now this has a didactic purpose. What's the purpose of showing this to you? Well, we're basically showing what happens when you set the slope to 0. You actually just get the intercept. So on question 4, the correct answer is 19.16, or the intercept. Question 3 is our imputed value. So expect these kinds of questions for the midterm and for the final exam. The kinds of questions where the logic or sort of the logic of kind of answering the correct question might build on itself. Okay, so for question 5, we ask, now suppose the percentage of people with HIV is 17.9, which is the actual percentage for South Africa, which is one of the countries in our data set. Now, what is the expected murder rate per 100,000 people based on the regression equation? Round your answer to 2 decimal places. Now, you could actually, if you follow along in Monday's section, you could actually follow along and use this code or use the syntax and derive the predicted values for every country and get our answer that way. But here, you don't have to make things that complicated. You can answer the question simply, again, by taking 17.19, multiply by the slope, which is 1.154, and then add our intercept, which is 19.161. And we should get an answer of 39.8 or thereabouts. And so what this really says, and you can validate this in the data set, is that the expected murder rate for South Africa, given its HIV rates, and given what we know based on the regression output, the expected murder rate is 39.8 per 100,000 people. And that's the expected murder rate, right? Now we know that the actual murder rate is 36 per 100,000 people. So then, given what you found in part 5, that is given the value of the expected murder rate, what is the residual? How do you interpret this residual? Now, you don't have to write this out, but the residuals are errors. I'm going to type it out for you just so you can sort of get a little bit of context here. Is basically this equation right here, which is E of I or EI minus EI. So I'm going to type this out here. And that equals the residuals or errors. And what that is it's a difference between our predicted values and then our actual values. Difference between predicted and actual values in simple linear regression. Okay, so conceptually we can sort of see E of I, or is basically each Y of I minus its, we can say Y of I predicted, I guess. We can say predicted minus Y of I actual. You could say something like this. So what is each? So we're basically asking you to do some simple math here. Now, behind that simple math, of course, is maybe something a little more conceptually more complicated, or perhaps less intuitive. It's really the idea that for every value between our x variable and our outcome variable, we can basically difference the predicted value and the actual value to determine what is each residual. So given that our actual rate is 36.17, and given that our predicted value is 39.81, our answer is simply that difference here. So it's basically, if I can write that out, it's that right there, about negative 3.1. Now, this tells us that our model is over-predicting the murder rate for South Africa. That is, the observed rate for the murder rate is lower than the actual murder rate. And I actually should say, I should probably say we subtract the actual by the predicted. The actual ordering of the difference doesn't matter. Take any value -1, but it does matter in terms of the reference point. When a model, you want to take the actual and subtract the predicted. So I apologize for that bit of confusion. The reason is that an over-predicted regression value is a negative residual, and an under-predicted value is a positive residual. That is, it's the actual value lies above the predicted regression line. If you have, say, 2 points here, see if I can draw. I'll try my hand at drawing just a simple straight line. Let's say we have a simple regression line that describes the association between 2 points. We might have a residual that lies above that regression line, in which case it is positive. If that residual lies below, then it is underpredicted by the regression line. Here we have a negative residual. That is, we take the actual value minus the predicted value, and the predicted value is just what we'd expect along this regression line. And then we find that difference here. So this is where the order actually matters. Now, when you talk about the math of statistics, or when you talk about deriving what is a simple linear regression, the order actually technically doesn't matter. The difference is sort of a difference. It's all relative, you could sort of say. But in this case, in terms of interpretation, keep in mind conceptually just what the difference is between a positive and negative residual, or an error is. Now, here's a red flag here, right? Notice I use the term residual here quite frequently, and so do we in class, but keep in mind we're going to also talk about this in terms of errors, and you'll probably run into this quite a bit in class, or sorry, in your statistical career moving forward. Here's a caveat, right? What is an error? Well, it's not a mistake here, right? This is the difference between conceptual or sort of technical language, or sort of the peculiar language of a particular culture, right? In this case, the culture of a statistician, as opposed to the culture of, say, human language. So when we talk about errors here, just keep in mind this is a term that is going to be used frequently, and we're going to build on this, what an error is. But keep in mind we're not talking about mistakes here. In fact, errors are something that to be expected in the data. The data is there's always signal and there's always noise. If you ever follow politics, you might have heard of Nate Silver's work, and he's a statistician who did a lot of claims at prediction, and was pretty successful until the last election. But he wrote a book called The Signal and the Noise. And I often think about errors in terms of noise, but not exactly. But I think it's a good way to think about it, because the signal is in essence sort of saying, what is the underlying pattern? And noise we kind of think about statistically in terms of errors. That is just, it's kind of the values that might bump up, down, or down the regression line, but that's where the data are. So the idea here is essentially, conceptually, when we talk about residuals or errors, we don't think of these as errors as undesirable. It's just that they are not necessarily, how do I put it? In the aggregate, when we add up all these values, they're not of key importance to us. In fact, the key source of our focus is actually on sort of the signal itself. What is the regression model? So that's just something I think I would emphasize here. Okay, and I think this will come clear when we talk about interpreting regression output here. So here you see the what you can actually easily create with the code here. You see a simple regression line produced in R between 2 variables. You have the predictor variable, which is always in the x-axis, and the y variable, which is always in the y-axis. So that's 2 key concepts you need to know. Then here you see a slope. You see a regression line that's characterized by a slope that is at the angle, and then its intercept, which is the value of the y-axis when the x value is 0. And we know that that's just looking, even if I just cross these coefficients out, which we typically won't do, you'll see that we can already divine that it looks like our intercept here, well, that's interesting. It looks like our intercept here would be probably a little bit higher, but it looks like we're not going all the way down to 0 here. So the key issue here, it looks like our lowest value is 5. It looks like this x-axis doesn't all the way go down all the way to 0. And we can see this because it's the intercept is between 40 and 50. It would look like if we assume that this x-axis is 0. In fact, it's a little bit higher. In fact, it'd be right around here. So the point is, and that would make sense, right? Because we have 0 to 5, 5 to 10, 10 to 15. The point is, don't always look at your output and think you can always divine what the intercept is, but just take a look here because you can see that the values of the x and y axis matter. And if the x-axis is not bound by 0, then we're not actually printing for you the actual intercept. But conceptually, the intercept would be somewhere around here if we showed the 0 value on the x-axis. The slope, however, is seen throughout the regression line, right? It's something characterizing the line. No matter where you are, it's always going to be negative 3.3. That is, for every 1 unit increase in the elderly population, the murder rate decreases by 3. Just think of this as, I always conceptually think of this as like little, how would I put it? Little staircases. A 1 unit increase here is a discrete decrease in our elderly population here, even though it's characterized by a continuous regression line. Okay, the residuals here, right, would be just this value, has a positive residual. This value has a negative residual. This is positive. This is negative. Negative means you're underpredicted, and positive means you're overpredicted. And finally, notice that the slope here, unlike in the previous questions, and I think even in the country data set, we actually, with the code that we had used, you see that the slope is a negative here, which means that it is a decreasing rather than an increasing line. So there you go. What is the equation for the regression line based on this model? Well, okay, at this point, I hope it's a little more clear for you. Slope plus x-axis, the x variable rather. So slope times elderly population plus the intercept, 58.07, equals the murder rate. And the murder rate is always the y outcome. And you can see that here, even in our answers that we provide, we're always giving you the murder rate, but the differences might be, well, what is, first of all, you never have that's technically a dash, or maybe 2 minus signs, but typically you don't have any negatives here. Even though the slope is negative, you actually, you want to actually have the, this is going to be the right answer here. Hold on. Yeah, this is going to be the right answer here. Maybe it looks a little weird here, but this is one negative sign. So it's 58 minus the value here times the elderly population variable. Now this might be a little tricky. Well, how do we know this to be the case? Well, as I said before, you have the slope being a negative value here. So it's not always going to be positive. It could be negative. So you just simply take the slope, you add a negative value, which is in essence subtracting its value, and then multiplying it by that x variable. Now the intuition here is, in essence, what is to think about what is the purpose of the regression line? Well, it's to make predictions. It's to make predictions in particular for the murder rate variable. You can't do that with any other expression other than the information used to describe the regression line. And that's, again, this intercept plus this negative value times the values that we have for that variable itself. So notice I'm saying plus and then I sort of pause and then say negative value. Because if you add something that's negative, it's a negative value. I hope that's pretty clear. I know it can be a little confusing, but then we ask you what for the slope of the regression line. Here, we're not asking for the absolute value. We're actually asking for the absolute value plus the direction in which the slope is going. So the slope can be positive or negative. So just to describe fully the slope, we actually want you to have the negative value here. So the slope is negative 3.339. So this tells you that for every 1 unit increase in the percentage of elderly people, the murder rate drops by about 3.339 per 100,000 people. So that's what it would do. Now, if it were any of these values, it doesn't actually make any sense because, first of all, these are the intercepts, and second of all, they just don't describe the data. But also, if it were positive, if we had a positive value for the slope, then it would say the opposite that we want to say. In other words, it would actually claim, if we claim that the slope was a positive 3.339, as that first option would indicate, then it would tell us that for every 1 unit increase in the rate of for every 1 unit increase in the percentage of elderly people, the murder rate increases by 3.339. That's not the case, though, and we can see that by the direction of the slope. We can also see that, hopefully, by the logic of writing out the equation, but also by the fact that we have a negative slope here. So I hope that's clear. Now, what is the intercept? We ask you that for question 9. The intercept is 58.074. And what does that mean? It tells us that the expected murder rate when there are no elderly people is 58.074 per 100,000 people. And now we tell you what the R squared is, and we ask you to interpret this. And I would interpret it this way, just to tell you that, and this should be multiple choice, it would tell you that about 70% of the variability in murder rate across the countries in our data set is accounted for or explained by our variable elderly population, or elderly pop. This suggests that the regression line closely fits the scatter plot data. So, and an R squared of 0.70 is rather high. An absolute a value of R squared would be 1.0, and an R squared which explains 0 of the variability in murder rate would be 0. So R squared is bound by 0 and 1, similar to a coefficient for our correlation coefficient. The main point here is that an R squared is always positive as opposed to positive or negative. And the R squared is actually describing our linear regression line. And that's very different than saying two variables are correlated. Here we're actually saying, using a different kind of intuition or a different logic of describing that linear association, we're actually saying, what is it that about, given our knowledge of a country's elderly population percentage, what does that tell us about our Y variable? In other words, given our predictor variable, what does that tell us about our outcome variable or our Y variable? So, now we ask, for the next question, we ask, what is the proportion of variation that is not accounted for or explained by our regression model? As I hinted to in Monday, it's going to be 1 minus 0.70 for question 11. And not only do we mention that in the modules, but it's also something that I think is, I somewhat describe in the output. And the point here is that the proportion here that is not accounted for is about 30% of the variation. So, yeah, to calculate this quantity, we simply take 1 minus R squared, which equals 0.3. So that's 30%. So to give an example for 10 and 11, if we had a R squared of 1, then the proportion of variation in our outcome variable not accounted for or explained by our regression line would be 1 minus R squared, or 1 minus 1, which would equal 0. In other words, 0% of our variation in our Y variable would be unexplained by our regression model if we had an R squared of 1. You very rarely see an R squared of 1. An R squared of 0.3 is okay, I would say. An R squared of 30% is okay in practice. Don't be surprised if you see an R squared that's lower than that in practice. For the purposes of this class, just keep in mind that what an R-squared is, how to interpret it, that it is a proportion that can be expressed as a percentage of the variation in our y variable, or our outcome variable, that is explained or accounted for by our x variable, and that it can be described both in terms of its value, but also in terms of the unexplained or unaccounted for proportion, which is the 1 minus r². And that's called the coefficient of determination when we talk about what is explained for in the model, and the coefficient of alienation when it's not accounted for or explained by our regression model. Then we ask a question that I think is might be relevant for the final exam. We sort of emphasize that this relationship is there's a negative linear relationship between elderly population and murder rates, and we emphasize that this is not necessarily causal. That is, there are other variables that can explain the association between the x variable and the outcome variable. Then we ask you, how do you describe the method of least squares to a fellow criminologist? This is a rather hard, difficult question. I think we give you 1 point here, but it's difficult if you get trapped up, I think, here, if you get trapped up in the jargon here. The key element here that I emphasized earlier in the week is that our method for the simple linear regression is to essentially find the values of the intercepted slope such that the sum of squared errors is minimized. That is, no other line fits to the scatter plot will have a larger sum of squared errors. So this is something we try to minimize, and in fact, you can use calculus to try to minimize it. You just find the minimum of the sum of squared errors. It's not something you have to do here, but that's essentially how we assess what it is. So of these answers here, it looks like the method of sum of squared errors is, it can be a little confusing to reread this, I think, but you just want to make sure that, I think there are a couple of trip ups here. We emphasize the word minimize, and then we alternate between minimized and maximized. So you want to make sure that we're using the correct word minimized here. That reduces your options to 3 here. But you want the other answer that is correct is that we have the smallest, no other line will have a smaller SSE is not correct. We want to say no other line fit will have a larger SSE. We're minimizing the sum of squared errors. That means none other will be larger. And this is, I think what's difficult here, actually, what I want to emphasize is not only the jargon, but the fact that these sum of squared errors, I think we're using a method to minimize them that we don't cover in the class. But just keep in mind that the key point is rather intuitive, that, and the correct answer is right here, which is that no other, the method of, it's the first answer here. The method of least squares of finding the values of the intercept and slope such that the sum of squared errors, SSE, is minimized. No other line fit to the scatter plot will have a larger SSE, or sum of squared errors. Now, sum of squared errors is basically describing what those residuals were. Notice I spent some time covering what that scatter plot was, what information we could derive here. I also spent some time stalling on this idea of what an error is and how it's exchangeable with a residual. This is because we both cover this in the module, but also it's an important key point in the course, which is that we take these sum of squared errors. So we take these values that are both positive and negative, we square them. So we just take this value, subtract the predicted value for the line, and then we'll square that value and we'll put it over here. We'll take this value, its predicted value, subtract its actual value, square it, put it over here, and we'll take that for every data point. And you could do this manually. In fact, you could do from our derived countries data set. And then you add those squared values, and then you want to minimize those values, and that's where that line balances between going up in some places and going down in others, and being influenced by some points more than by others. The point is that the line tries in the best way that we can, using sort of this really simple algorithm, is probably the first algorithm that you're encountering in this class. The algorithm attempts to minimize those squared errors so that this line is the best linear fit to the data. So it makes us several assumptions here, right? Basically that all the data are relevant, that namely as well, I would say it also makes the assumption that we can fit and describe this association by two variables, and that these two variables have a linear association. Those are some big assumptions, and those are assumptions that we need to check, because, for example, if we look at this data set here, we see in our country level data set, there seems to be an outlier, at least when we look at elderly population and the murder rate, that seems to be less, I guess, applicable in terms of our linear fit model. That being said, you can see that most data points fit pretty well here, right? Most are relatively well predicted by the line, and some are very close. So that's what the regression model will always do, no matter what data points, no matter what junk you give it. It'll always try to minimize those sum of squared errors. It's an algorithm there. It's a pretty heartless algorithm. It will go through and do that regardless. And we sort of answer some questions, I think, for 13, whatever, questions 14 through 17, emphasizing, I think, these points a little bit further, but let's take a look at this. On question 14, after looking at some outputs, looking at murder rate and internet, we ask you for the equation for the regression line based on this model. And I hope this looks pretty familiar. It uses quite similar data that we have access to. So you could even, if you wanted to, you could double check this. Again, it's not required. But let me read to you this prompt for questions 14 through 17. Basically, we're saying, hold on, sorry. Basically, we're stating, you believe that access to the internet reduces criminal activity through a substitution effect. That is, you think that greater access to the internet will decrease the criminal activity because people will be spending a greater proportion of their time online. Okay, so if it's a substitution effect, that means greater access to internet will decrease criminal activity. That means the more internet access a country has, the more time they will have online. Therefore, there'll be a decrease in the murder rate. So we should have a 1 unit increase in internet access should lead to a decrease in the murder rate, a drop in the murder rate. So we should actually see a negative slope here. In fact, that's what we see in the output here. Now, if you notice, there are a couple attributes here. Just from the coefficients, we see that the intercept shows that even when internet access is at 0, we still have a relatively high intercept here. We have a high value for murder rate, a relatively high value for murder rate, even when the internet access is equal to 0. Again, we ask you what the equation is for here, and we simply take this intercept, we add to that intercept the slope, and then we multiply that slope coefficient times our x variable, which is internet. So we simply take internet times our slope, and then we have that intercept here. So it's actually going to be 38.2642 minus 0.3668 times our internet variable. The key point here, as we emphasized before, is that our slope variable is characterized by both its absolute value, that is its numeric value, as well as its sign, whether or not it's positive or negative. So here we have a negative value for our slope, so we simply take our intercept minus and make sure that we have that minus value here. Okay, so here we have the equation. Then we ask, on question 15, we say, the percentage of people in the Ukraine with access to the internet is 22.55. What is the predicted value of murder rate for Ukraine using your regression model? And basically, we're going to use some math here, and we're going to basically take that regression line, and here I have it typed out. Basically, we take our value from the regression line, and then we substitute our value of 22.5 for our x variable. So first I have right, we have our intercept here, we have our slope here, which is minus this, and we multiply it, and with the value of our internet variable here. And this is equal to the murder rate. That's why our correct answer, question 14, is here. And our answer is about 30.00. Now, what is our residual here? Let me clear out that typing here. The residual here is simply the actual, for question 15, 16, we actually give you the actual murder rate. We say the actual murder rate is 6.2 per 100,000 people. What is the residual or error for Ukraine? Round your answer to 2 decimal places. Well, that is actually simply 60 minus 30. So the residual here is actually, let me type this out just to be clear. Hold on. Sorry. I think I accidentally typed my, this is the problem about using Mac. I accidentally typed out my Siri. Press my Siri button. I don't need that. Our actual murder rate for, the actual residual or error term, or error rather, the actual residual or error for Ukraine is 6.20 minus 30.01, which equals negative 23.81. So just to conceptually understand this, what does this say? This says the regression model is over-predicting the murder rate for Ukraine. That is, the predicted murder rate is 30, but the actual murder rate is 6.20. So its negative value suggests that we're actually over-predicting by a considerable amount the actual value. And that's what a negative residual is. Positive residual says we're under-predicting by our model. Okay. Yeah, I should say question 17 asks us that. Is your regression model over or under predicting the murder rate for Ukraine? Well, because our actual value is less than our predicted value, our predicted value is, well, here, because our, hold on for a second. Did I just not remove that? Okay, well, it doesn't matter. I'll clear everything here. Because our regression model is, our model, so the correct answer for 17 is going to be over predicting. And we're over predicting the murder rate because our actual murder rate is 6.20, but we predict it to be 30.01. So we're quite off. We think it's much higher than it is. So just keep in mind, high negative values, negative residuals indicate an over prediction. Positive residuals indicate an under prediction. Again, negative residuals equal an over prediction. Positive residuals indicate an under prediction. It's easier to describe in the specific. Just think about what is the association between, or what is the relation between a residual and the actual value for every country or the country in question. Here we have a model that over predicts because it is much higher than what is actually the case. Okay, question 18 asks, based on this regression model, you find the residuals or errors for all the countries in your data set. And here we list those residuals. So again, following this kind of mini mission, we could say, of looking at internet use and its association with violent crime or murder rate, rather, we find that for most countries, there is a negative association. Sorry, there are negative residuals. Looks like 1, 2, 3, 4. Was it 1, 2, 3, 4? No, 5. It looks like most have negative residuals. 1, 2, 3, 4, 5. And 3 have positive residuals. However, one of those residuals, positive residuals, is quite high. If you look at Jamaica, it's 42 about. So is your model better at predicting the murder rate for some countries that, sorry, we state that your model is better at predicting the murder rate for some countries than for others. That's true. Which country lies closest to the regression line? So as I pointed out when I showed the data, I think for a different variable, ones that were graphed, these data points that lie close to the regression line, whether they're positive or negative, right? They're negative if they're below the line, positive if above. Those data points are close to the regression line if they have small absolute values. That is, we subtract or add them, whether the difference is positive or negative, rather, each residual or error is going to be relatively small. And the absolute value, whether or not it's above or below the line, the larger it is, the less close it is predicted by the regression line. So I just scrolled up to show you that graph, that figure, if you don't want to look at the analysis in R. The point is, the country that lies closest to the regression line is going to be the one with the smallest absolute value. In this case, the correct answer is South Africa. And the country that lies farthest from the regression line is going to be Jamaica. So they both have positive values. And I would ask, what does that further mean? Well, it means it's underpredicted by the regression line. In Jamaica's case, it's vastly underpredicted. In other words, we predict a much lower murder rate than actually exists in Jamaica, given its given its rate of internet use. Whereas South Africa, given its rate of internet use, were very well predicted by the regression line. There's a residual for Ukraine, by the way. So in fact, if you wanted an answer, I guess, for, well, this could be for a different question, I'm not sure, but the point is that residuals are, the absolute value of residuals will tell you how close or how far they are from the regression line. So then in our last question is multiple choice. We ask you to calculate the average of the residuals. The average is a little tricky question. It is worth 1 point. The average of the residuals is going to be 0. In fact, that's the main point here. You can actually add these up here. I'm not going to do it here, but it should work out. The average of these residuals should be actually 0. Now you don't have to do that. People were asking about that, and that's not the case here. So the average of the residuals is 0 within rounding error is something you need to know. You don't have to really solve anything. And this is because the positive and negative residuals cancel each other out. And that's why we need to square them. Squaring the residuals makes them positive so that we can actually calculate an average that we can then minimize using the sum of square errors. So I think I have quite a few questions about that, but hopefully this clarifies that. The rest of these questions we addressed early in the week using the outputs, which I think are pretty transparent. I don't think I got any questions about these in particular, except maybe for question 27. Writing out the equation for the simple linear regression line is going to be is going to be basically as you've done it in the previous question. So I think we're going to end right there. But if there are any other questions, please let me know. Otherwise, thank you very much. Do any of you have any questions about the material this week? Let's see. Sergey, you have an interesting question. Let's see what you have. What is specifically wrong with the youth? Thank you. Sure, of course. use of this use of the term regression analysis. Lecture video. Why could that be a multi-factor tax rates nonlinear regression analysis resulting? I think that's a very specific question. I think I wouldn't say there's anything specifically wrong with any particular term of a regression line. Oh, okay. I'll take a look at that example, but yeah, I'm not really sure that sort of deviates from the point of, I think, what we're trying to emphasize here, which is simply the main point is that when you talk about simple linear regression, got it. Okay. Well, I don't want to autoplay the YouTube video, but I will take a look at that, Sergey. Thank you. But the point I want to make here is that when we talk about simple linear regression, we're actually not using what is called generalized linear regression, which just can characterize our regression using a different shape or different slope. In this case, when we talk about simple linear regression, by minimizing the sum of squared errors, we're actually using what is called an identity or Gaussian link function, which actually characterizes the relationship as linear. So in a way, I think if without looking at the video through the YouTube link, to stay on task and sort of emphasize this, our role as a social criminal, sorry, as a criminologist, the emphasis on the simple linear regression and minimizing the sum of squared errors. And the case of the ordinal least squares option, or the OLS option as we call it too, or ordinary least squares option, is that every other regression example that we look at, if we look at, say, categorical outcomes, let's say we have a categorical outcome that has two categories. Let's say whether or not somebody had elected, say, voted Democrat or not, or in the case of murder rates, let's say we wanted to predict whether or not the murder rate was above or below a certain threshold, say the median or the mean. Then we're looking at a generalized extension to the linear regression model. So the way to think about the linear regression model is, in future analyses, is actually think of it as maybe we could think of other extensions as sort of a generalized expression of the linear model itself. So without looking at the video, I'd simply say, in so many words, the simple linear case is one that's extendable to other nonlinear cases and nonlinear regression cases. So I'm loath to say that anything is incorrect or specifically wrong about regression models per se when we characterize an ordinal outcome, like a yes/no option, or to characterize even nonlinear outcomes, such as thresholds, or even, oh, I don't know. Yeah, I would say just exponential functions, for example. So that's what I would say, is that we can think of regression. That's the beauty of regression, is that it's a very flexible model that you can apply to other cases. And as I said earlier in the week, it's a workhorse. That is, it's something that is a statistical model that is going to be flexible, that you're going to apply to almost everything that you do moving forward. So thank you very much. And I'll stop the video here. Oh, thank you. I think that's a procedural question. I will answer that, but let me just stop the video for a second.